Hi everyone, and welcome to the section 7.1 video on differential equations. So the next few sections we're going to be going through this idea of a differential equation. It's a pretty neat set of sections. There are many classes you could take where you learn about how to solve these, how to explore them, all kinds of crazy stuff. So this is going to be a very, very surface level overview. And we're only going to kind of scratch the surface here. But it's pretty interesting, and hopefully you'll be able to find something that you're interested in, adjacent to math, maybe in one of the sciences, economics, something, and you can do a little digging, see how it connects here, and find some cool stuff. So always happy to answer questions on that. But let's actually get into what this is. So right down here we have this definition and then some examples. So what does this say? A differential equation is an equation, okay, so there's going to be an equal sign, that's good, that relates a function to one or more of its derivatives. So this is really it. What is a differential equation? It's just an equation that has a function and a derivative inside the equation. So it's an equation with a derivative in it. Okay, that's it. That's what a differential equation is. It's an equation. It's got a derivative. So here are some examples. I see a derivative here. I see a second derivative. Sure, that's a derivative. Why not? I see a derivative here. You'll notice a lot of different stuff in here, right? There are constants. K and M are these constants. So at the beginning of a problem, we would define these as just, this is, K is going to be a fixed number for the whole problem. M will be a fixed number. Then there are variables. P often stands for population. And then another variable here, T. T, when you see it, not always, but usually stands for time. So this first differential equation is trying to describe how P for population is changing over time, which is t. Now, why am I saying specifically that this equation is talking about change? Well, that's the whole point of the derivative, right? The derivative talks to us about change, so a differential equation is doing exactly that. This says the change in population with respect to change in time is equal to this equation. So what we can do is, given a population value P, whatever you're looking at, bacteria, mice, people, whatever, you can put that number in. If you know K and M, these constants, then you can calculate what this is, and you will know how that population is changing at that time, that instant in time, because that's the derivative. So these equations then are extremely useful for describing any situation where there is change. That's it. That's a differential equation. So I'm trying to describe something that's changing, and if I can write down a formula for how it changes, I can use that, just like we've been talking about using derivatives in the past and antiderivatives. So differential equation, all right? An equation with a derivative in it, boom, that's the whole thing. The simple definition, but you'll see kind of how crazy this can get. So okay, let's keep going down here. So these differential equations, the one we're going to run, the ones that we're going to see, have solutions. And we need to talk about what it means to be a solution. So we got to kind of, think about this a little bit, right? Let's go back up to this example real quick. I'm telling you that there is some population P that's changing over time. So if I tell you that, it's very natural with all of that we've learned in Calc 2, Calc 1, Pre-Calc, all this stuff, for you to say, okay, give me this, right? You're telling me population changes over time. That sounds like a function, so tell me what the function is. This P of t here is going to be the solution to this equation. And that's, often the goal. It's not always very easy to do, but that's often the goal, is I might be able to describe how something's changing. Okay, that's great. That gives me a differential equation. But really, it's nice to know how this bacteria population's changing. But if you could just give me a formula that describes just the population itself over time, that would be better, right? Give me the actual population equation, not just the differential equation. So our goal is to solve these equations when possible. And so what is a solution going to look like here? Well, what's going to happen is this function, this solution, will satisfy this formula. So maybe like, oh, what do you mean satisfy? Here's what I mean. Let's look at this formula again. The derivative of p with respect to t. What does that mean? That's p prime. Take the derivative of this function, the solution. That's what this says to do, right? It needs to satisfy this formula. So whatever function you think might be the solution to this differential equation, you take that function, and it's just going to be, some function of t. You take its derivative, set it equal to this, and if this checks out, you have a solution. That's what it means for a function to be a solution. It means you could plug it into this equation. You got to do the derivative over here, and you have to put it in here and put it in here. If you do that and the equation checks out, you've got a solution. Okay? So it's called a solution if it satisfies the differential equation. Basically, this is trying to tell you how a function p will change. If you can find a function that changes like this, you got a solution. That's it. We're going to be able to see that graphically as well as just kind of thinking about this, using calculus only. So that's going to be nice. And once you see it graphically, I think it's like, okay, I see how there could be a solution and, kind of how that fits. So I think the pictures will be nice. So we'll get to that. Okay, so we're going to do a bunch of examples, but for now, it seems maybe a little abstract, but we'll just keep going. Okay, so we are often then going to be asked to solve a differential equation, which means we have to find any possible solutions, as we described above. An actual function that satisfies the differential equation, changes just like that equation tells me it will. Okay? So again, it's going to often be of this form, derivative equals some function, right? So we actually have done this a bunch of times. We just didn't call it this. So you might be like, no. Well, hold on a second. We did. So let's look at this example. Y prime equals x cubed. And let's just think about what we're saying here. And you could change the notation if it helps you. So dy dx equals x cubed, right? Or you could do this differently. The derivative of some function f equals x cubed. And I think maybe if you didn't see what was happening now, this is the one that might get you there. What is this equation saying? It's saying when I take the derivative of some function f, I get x cubed. You might be like, wait a minute. Am I just doing the antiderivative? Because that was how I tackled this before, right? When we first talked about antiderivatives, it was, okay, I take a derivative, I get x cubed, so can I work backwards to what this is? Yeah, that's the whole point of the antiderivative, was to get you back to this f. Well, that's exactly how you can solve some of these. Not all of them for sure, but some of them in a simple enough form like this. It's just asking you, hey, the derivative or change of this function is x cubed. What's the function? Well, we know how to do this. The antiderivative of x cubed is x to the fourth over 4. There you go. So this function the change of this function is given by x cubed, right? We know that rule. So that makes this x to the fourth over 4 plus c a solution to this, because this equation tells me exactly how this one changes. Boom, differential equation solved. So hopefully that's like, oh, okay, I've seen, okay, fine, I've seen that before. Obviously, Mr. B is going to make this crazier, and yes, I will. But, just right at the beginning, simple idea, we've done this before. Okay, basically you're thinking like, yeah, I've integrated. Cool. Okay, there's a couple things we have to talk about here, all right? Now, one of them, and there's a little discussion in here, right? So it's not easy to do this in general. We'll have to learn a couple techniques, just like, integration. It's not easy to go backwards from taking a derivative always, so we learned some tricks or tips or tools or rules or whatever you want to call them. We're going to do some of that, not a lot. You can really go crazy into that, but we're not going to do that a ton, just a little. But the other thing that we have to point out from this equation is that I think can be easy to miss is right here. We're used to just like, when you first learn antiderivatives or taking an integral, you just were told, don't forget your plus c, don't forget your plus c. Well, what does that mean here? You got to think about that a little bit. And it's a little weird, I know, because it's kind of goes against what you might be used to. We had this equation. I told you, let's solve it. Well, what does that usually mean? Usually you mean, okay, I solve it, I get one solution. Here you go, x to the fourth over 4. But that's not the case here. There's many, many, many functions that when I take the derivative, I get x cubed, right? Just plug some values in for c. So we could do that. How about this function? Y equals x to the fourth over 4 plus 3. Take the derivative. Y prime equals 4x cubed over 4. Derivative of a constant 0, right? Oh, okay, I see it. X cubed. So it didn't matter what I put here for the c in terms of what constant, because it doesn't actually do anything in terms of y changing. So we often can get a very large, infinite in this case, family of solutions. Many, many, many solutions to these. And so that might seem not helpful. Like, okay, I have this differential equation. Maybe I'm trying to learn about population of bacteria, but you just gave me infinite solutions, so thanks for nothing. Well, we just have to take an extra step to narrow it down to one specific solution. All right, and so we will get to that in just a second, but that's something we have to think about when we see, an extra constant pop out here. Like, what do we do with that? Okay. Now, how do we deal with that plus c? How do we deal with, actually finding one equation for this population or whatever we're dealing with? Well, and you can read through here, but basically what we have to do is give something called an initial condition. And again, I'm going to keep using population because it's just I think a good one to use as the example kind of in your head. But what you can do here, and again why I like it so much, is to figure out, which of these infinite many solutions is the right one for me in my exact scenario. I have to have a piece of information to start about the population. And this is often called an initial condition. So this could be something like, what is the population at time 0 in your experiment? So if we're doing an experiment with this bacteria, and we start the experiment and we know we have 100 bacteria. Okay, that's an actual piece of information I have. It's an initial condition. I also know how the bacteria will grow. That's given by the differential equation. From the initial condition and the differential equation, I can solve for a function that will completely describe the bacteria as time passes. But in order to fully get that function, I need to solve the differential equation and have this initial condition. Okay? So that's, you got to kind of think about, I've got infinite number of solutions. How do I narrow that down? Give me a piece of information. All right, so you can kind of read through here, but that's the general idea of that. So let's just try some problems. I've talked for enough, right? 15 minutes of talking. That's usually better than I do maybe, but that's okay. So this first problem says, verify that y equals negative t cos t minus t is a solution of this initial value problem. So again, what do I have? I have a differential equation, dE is the shorthand for that, and I have an initial condition, IC, initial condition. So this should be good enough to get me a solution. So I'm not actually going to solve this one by hand. I'm just going to verify it works. Well, how do we do that? Well, you take this function and you, in essence, plug it into the differential equation. So, okay, start going. T, that's a t, good, I got it. dy dt, oh, I have to take the derivative. Okay, so maybe over here I'll say, well, what's y prime? Well, I got a new product rule here. So that'd be negative cos t plus, and then we've got derivative of cosine's negative sine, so that'd be plus t sine t minus 1. So make sure you get your practice in, do that out. Okay, so then that all gets plugged in here. Wherever this dy dt was, right, this whole thing, because that is dy dt, gets plugged in, plus t sine t minus 1 equals, okay, now plug in y, negative t cos t minus t, and then plus t squared sine t. Okay, now how am I going to know that this is a solution to this? Well, I plugged this specific y into my differential equation, and now I just have to make sure that this equal sign works. So algebra, that's it. Just do some algebra. Make sure that the two sides are equal. So, okay, negative t cos t, and then multiply the t in, plus t squared sine t minus t. So that's t in there. Now, is that equal to negative t cos t minus t plus t squared sine t? I don't know. Let's look. Negative t cos t, negative t cos t. All right, 1 for 1. T squared sine t. Oh, 2 for 2. What is left? Finally, I got a negative t and a negative t. Haha! Check. Left side equals right side. That means this function really does satisfy this differential equation. So this differential equation does describe the change in this function. Does accurately describe it. Okay, what about the initial condition? Well, we just have to make sure that this function actually satisfies this point here, pi comma 0. So this is telling me pi comma 0 should be on this curve. So let's just check. Plug pi in. So the initial condition, check now. Y equals negative pi cosine pi minus pi. Well, that's equal to cosine pi. You're at 1, you go halfway around the circle, you're at negative 1. So that would be negative pi times negative 1 is pi, minus pi equals 0. Hooray! I plugged pi into this, which is our y, I get 0. There you go. So you verified the solution. This is legitimately a solution to this differential equation. Okay, what's next? So let's go down here. Number 3, it says, for what values of r does the function y equals e to the rx satisfy this differential equation? Okay, so we have a differential equation. Now, we don't have an initial condition, but that's okay, because that just means that we can have very general solutions. We don't have a specific one. So how do I know if this satisfies this? Well, plug it in, right? That's what we talked about. Just plug it in. So this gets plugged in. So 2, y prime, I got to do that. So let's do y prime. We can do it down here. Y prime, this is y double prime, so I got to do it twice. This is r e to the r x. Y double prime equals r squared e to the rx. Okay. So then what was y double prime? Okay, that was r squared e to the rx. Remember, r is just a constant here, right? R is just a number. That's why I'm treating it that way here. Plus y prime. Okay, r e to the rx. Just plugging that in. Minus y was just e to the rx equals 0. Okie dokie. So you might be looking at this like, oh, geez. How do I make this 0? Well, factor out the e to the rx. We do a little algebra. So this is 2r squared plus r minus 1 e to the rx equals 0. Now, got to think about this a little bit here. This piece, never 0. It's e to the rx, never 0. So then what I need to make this 0 is I only need to say, when is this going to be 0? Right? That's what I need to solve. Okay, so we got to think about this. When is this thing going to be 0? Well, this is just a quadratic, so you can solve this for when it's 0. You can use the quadratic formula. You can factor it, whatever you want to try to do. So we have 2r, r. Okay. So when we plug this in and do the multiplication, we're going to need a positive r here, and then these two numbers are going to have to multiply to negative 1. So then this should be a plus 1, this should be a minus 1. So let's see. 2r squared, boom. 2r, it's a positive. A negative r will give me a positive r, awesome. And then when I hit these two, negative 1 and 1, I'll get negative 1. Okay, so that's equals 0, which means r can be equal to negative 1, or r can equal, I just have to solve now this one for 0, 1/2. So there are actually two values of r here that will solve this specific differential equation. So that's kind of interesting. Because above, let's just zoom back above for a second. Above, we saw this simpler looking differential equation, and there was one function with just, a shift up or down, right? This solution is really just one function. It's infinite number, but they're all just shifted versions. That's not the case here, right? Let's go back down to this one. That's not what's happening here. R equals 1 and R equals negative 1, and r equals 1/2 are very different, right? What is this telling me? It's telling me y equals e to the negative x and y equals e to the 1/2 x both solve this differential equation. These are very different pictures. So this hopefully is starting to get you to see how things can get a little more complicated. It's not just like, oh, I get this one solution, infinite copies. We can start to have multiple different looking functions still kind of fit these pictures. And again, when we do it in the next section, we'll start looking at the graphs. You'll get a sense where you'll be like, okay, I see how for one differential equation, I can have multiple different types of solutions. So you'll see it. For now, just believe me, in the math, it's right here, so you can believe that. But when we do the graphs, you'll be like, okay, I see what's going on here. Okay, so B says, if R1 and R2 are values of R that you found in A, so negative 1 and 1/2, show that every member of this family is also a solution. So this is another super, super cool thing. And, I'm just going to briefly talk about this one. We don't, this is more advanced than we're going to get in this class, but it's a cool thing to see. What this is saying, what is it saying? This is saying that I can take a solution to a differential equation, multiply it by a number here, okay, this kind of constant here, add it to another solution, and I still get a solution to the differential equation, which you might be like, what? But I know, it's crazy. So again, very, very insane, but this is what we're going to show right now. I'm going to take two different solutions. So ae to the negative x plus be to the 1/2 x. I've taken two things I know are going to be solutions. I've done what's called a linear combination of them, okay? And that's also going to be a solution. So watch this. Crazy, I know. So we're going to take this 2y prime, 2y double prime, plus y prime, plus, or I think that's a minus, equals 0. Did I mess that one up? Minus y. Whoopsie. So that's our differential equation. So we want to show that this is a solution. Okay. What do we do? Well, we've got to plug it in. So y prime would be negative a e to the negative x plus b over 2 e to the 1/2 x. Well, we need y double prime, right? So do that. Y double prime is, drop another negative, a e to the negative x plus b over 4 e to the 1/2 x. Okay. So then what happens? Well, plug this in. So this would be 2 a e to the negative x plus b over 4 e to the 1/2 x. So that's just this right there. Okay, so that's going to be plus y prime, negative a e to the negative x plus b over 2 e to the 1/2 x. So y prime, minus, and then we plug this in, a e to the negative x plus b e to the 1/2 x. Okay, and I need this whole thing to be 0. Do you see it? It's kind of weird, but let's check this out. And I wrote it in a little funky of a way to see if maybe kind of writing it would help you see this. I have a negative a e to the negative x. I have a negative a e to the negative x. That's two of them. Well, would you look at this? I multiply this 2 inside. I'm going to have 2 a e to the negative x. This whole thing cancels. Okay. I have got a error. I have got, no one saw that, a negative b e to the 1/2 x, because remember it says minus the whole thing here. Okay. I've got a plus b over 2. So okay, I still have this extra, negative b over 2 here I got to somehow deal with. Right? But wait over here. The 2 again comes in. Come in here. So let's look. I have a full negative b. Okay, I've added a half b. And look at this. 2 over 4. That's another half b I've added. These all cancel. And there we go. All the terms cancel, give me 0. Check. I've got a solution. So you take your derivatives, plug it in, boom. So I can take what seem like completely different solutions and do a linear combination of them and get a solution back. Pretty cool idea, a little bit crazy. We're not going to dive into that. That's beyond what we'll do in this class, but pretty neat. So, okay, let's keep going. All right, so number 9 says, a population is modeled by this differential equation. For what values of p is the population increasing? So this is kind of cool. What's neat about these differential equations is you can often learn a lot about them and p, the function you want to solve for, by just looking at them and thinking about them. And just reminding yourself, what does this say? dp dt says the change in p, the population, with respect to t, right, is this. So, okay, for what values of p is the population increasing? Well, p increasing tells me the derivative should be greater than 0. That's our Calc 1 coming back, right? I think this is the second or third time in this semester we've used that same idea from Calc 1. It's a big one. So, okay, well, when do I figure out when the derivative is greater than 0? How could I figure that out without knowing p? Only if I had an equation right somewhere near that described the... Oh, it's right here. I just need this bigger than 0. Okay, well, it's being multiplied, so that's pretty easy. What are the two options? Option number 1, 1.2p is bigger than 0, and 1 minus p over 4,200 is also bigger than 0. I need to multiply these two numbers in both positive, or they're both negative. 1 minus p over 4,200 is also negative. Okay. One of these is complete baloney, and you need to throw it out immediately. Take a couple seconds to think about this. A population is modeled by this differential equation. Okay, why is this one baloney? Well, look at the first term. 1.2 times the population. You can't have negative population. It doesn't make any sense. So just throw out number 2. And this is something that you've got to be paying attention to. We're doing lots of applications. We're going to be doing examples with applications. You've got to think about the applications, the variables, what could they mean? In this case, p represents population. It's never going to be negative. So if you are in a situation where p is negative, you just throw that out. So, okay, that's not too bad. Well, like we just said, p is always greater than 0, unless, of course, the population is 0. So then this one's not too hard to do. I just need the population to be bigger than 0. Okay, this one I got to do a little work for. 1 minus p over 4,200, and we don't need the extra parenthesis for a moment. I want this to be greater than 0, so that means I need p over 4,200. I move this over. I need this fraction to be less than 1. Move the 4,000 over. I need the population to be less than 4,200, whatever. People, bacteria, deer, doesn't matter. So p, a population less than 4,200 will mean that my population is going to increase. Okay. And then you could kind of keep, going through here. When is it going to decrease? Well, do the same thing. For this to decrease, what happens? I need 1.2p times 1 minus p over 4,200. I need the derivative, which is equal to this, to be less than 0. Okay, well, we just kind of talked about how this is never going to be less than 0. So what I really need to solve then is, when is this chunk less than 0? Just solve. We just solved, actually, right, with this flipped, so you can just do the same thing. P over 4,200, move it over. Okay. Boom. If the population is over 4,200, then the population will decrease. So let's think about this. What is this model telling us? It's telling us there is a limit on this population. There is some number, and it just happens to be this one, 4,200, where that's kind of like the perfect population zone. It doesn't matter what population you're at. If it's not 4,200, we're going to try to get there. If your population is smaller than that number, the population over time will try to increase up to that. If your population is bigger than 4,200, there's too many people, deer, whatever, and the population is going to decrease towards that. So what we call that is an equilibrium solution. So this has a special name, An equilibrium solution is a solution that's hit that spot that, it almost feels like the differential equation is trying to get to. That's going to happen when the derivative is 0. But I have a formula for the derivative, right? 1.2p times 1 minus p over 4200. I want when this is 0. So, okay, how do I make multiplying two numbers 0? Well, there's cases. 1.2p equals 0, or 1 minus p over 4200 is 0. This one's not too hard to solve. The population could be 0. If there's no bacteria, you're not making more bacteria. They do not pop into the universe out of nothing. Okay, over here, we just solved this like a whole bunch of times. P is going to be equal to 4,200. There we go. If there are no people, no deer, no bacteria, whatever you're doing, then you're not going to make any more of them. You're at equilibrium. On the other hand, if you've hit 4,200 of your population, whatever it is, you're at equilibrium. It's going to try to stay there. There you go. So think about what we just did. That was a lot. We know where this function p is increasing, decreasing, and we also know where it kind of does this flat line where it's not going to move at all. So much of that just from using calculus ideas and this equation. Right? So we'll talk a little bit about what the solution to this looks like in a future section, because we can do it. In the next section, we'll draw some pictures with this so we can kind of extend what we just did there to visualize this. And I'll show you how to do that in Mathematica. And then we'll get to solving a couple of these and learn some methods that just use our calculus knowledge. It's nothing more than just we are going to use our knowledge of integration to solve some of these, which is cool. So, it's a very deep, very interesting topic. I'm gonna link a bunch of websites, videos, cool stuff where you can see more about this. Again, we're gonna do a very cursory view of these ideas, but hopefully you can find something interesting for yourself. Get some practice in with the homework, and as always, let me know if you have questions, and I'll see you in the next video.